Welcome back to this Robotics 2 lecture. Last time we have started seeing how to model the interaction between the robot and the environment. We have seen that there are many possibilities, and essentially we mentioned that depending on how we model the contact type with the environment, we implicitly suggest a way to control the interaction of the robot with it. And essentially there are two types of contact model, a very stiff one and a compliant one. Today we will see through very simple example what are the differences in models and how we control then both motion and interaction. In the first case, when we have a very stiff environment, this will induce a possible way of treating this is to consider the presence of geometric constraints, which are added to the free motion dynamics of the robot itself. And we will see how to model this in general. There are two possible ways of proceeding, namely considering a constrained dynamic model or projecting the commands in such a way that we are satisfy this geometric constraint, or using the constraint to eliminate some degrees of freedom of the robot. We will treat the mathematics of these two cases and then apply back to some few simple examples to illustrate how the method works. In the last part we will see instead the compliant case, and we conclude the lecture by introducing the concept of hybrid motion, so hybrid control of a hybrid task in which we can control both motion and contact forces. Indeed, this requires at least the presence of 2 degrees of freedom in the structure. So let's proceed with the first situation. Imagine that we have a very stiff environment and we consider just a two-dimensional case. The robot here is an idle one, is schematized by a simple mass subject to two Cartesian forces, Fx and Fy. So, in fact, this is an ideal case indeed, but we have seen already that as long as the robot is in free motion, we can apply feedback linearization in the Cartesian space such that the robot is reduced to a unitary mass or to a mass of any positive value. And this is exactly the case. So here we are considering, we may have started with a 2R robot moving in the plane, vertical or horizontal, we don't care. Feedback linearization has achieved this type of result, at least as long as the end effector is moving in free motion. Now, we forget for a moment where are we coming from, and we're getting closer to an environment which is represented by this gray wall, which is very stiff, so it doesn't undergo any deformation, and it's located at a certain position, let's say along the x-axis, so the xe of the environment is when x is equal to some constant c. The environment will not move. Now, the model that you see on the bottom would be the model when we get in contact with the environment. And we have indeed two types of situations. The first situation is when x, so the position of the mass along the x direction, we don't care about y in this case, is strictly less than c, then the environment reaction force, so the contact force that is being generated when you try to penetrate the stiff environment, is equal to 0. And so we have the conventional situation of a free mass moving in xy. Indeed, when we are in contact, so when the position x is equal to c, we have two situations. If we apply a force which is negative, then we will detach immediately from the wall and so we return the situation of free motion. Instead, if we apply a positive force or even a zero force, if we apply a zero force, we remain in contact. If we apply a positive contact, we try to enter into the surface, but the surface is very stiff indeed. So we will actually not move at all. Now, this simple assumption, modeling assumption, requires that, we implicitly assume that we get in contact with the environment at zero speed, so initially with x dot equals 0. If this is not the case, so we are moving in free space, approaching the surface with a positive velocity along the normal direction, so we hit the surface, we have an impact with the surface at a certain speed, then we can model this and simulate also this situation, assuming that we have an inelastic impact, which means that at the instant of impact, we will have a positive velocity, let's call it x dot minus, with a minus symbol. Immediately after, there will be a full return of energy, so the mass will have a negative velocity, let's call it x dot plus, so in the instant immediately after the impact, which is equal and opposite to the previous one. So we will hit and bounce back without losing energy. Instead, if in the impact there is some absorbed energy, the same will happen. So we will switch from a positive velocity x dot 0 minus to a negative velocity x dot plus immediately after the impact, which is strictly less, let's say by a factor beta less than 1 to the velocity that we had before the impact. So it's very important to model correctly this situation, but from now on we will assume that we get in contact at slow speed in a guarded motion, and we reach the contact at zero velocity, and from now on we try to apply a force, so an Fx larger or equal than 0. Then what is written on the slide fully applies. Now, if we are in this situation, of course, x dot will continue to be 0 and x double dot will also be 0. So what is the consequence of that? If we look at the original equation, being x double dot equals 0, then we have an algebraic relation between the reaction force Fe and the applied force minus F, because Fx plus Fe should be equal to 0. This shows that if we assume this type of stiff contact, and by the way, we assume no friction at the contact, on one side we have an equation which remains untouched, my double dot equal f of y, which is the free motion direction in a sense. So along this direction we don't care about the presence of the contact, and here is where the absence of friction during sliding along the contact enters. Indeed, we may also model friction at the contact, but then we should have an extra term in the second equation when we are in contact. On the other hand, the first equation completely vanishes, but provides us the information about the contact force. And for this particular case, the only thing that matters is the applied force Fx, so the command that we're giving to the mass. And this will be equal and opposite to the reactive reaction of the environment. Because the environment is infinitely stiff, in fact, in this modeling assumption, whatever force we apply, it will be returned instantaneously by the environment. Indeed, all assumption, this outcome assumes that everything is fully rigid. When the forces increases above some limitation, of course, this is just an ideal assumption, and there will be some deformation or some internal stress that will change the picture. But indeed, this will not be the case in most of the application. Now, I would like to make a jump forward to show in this very simple situation what is the alternative. Then we will come back to generalize this situation. So I'm using this callout function to move to slide 38. And this is the other possibility of modeling the same situation. So the model is exactly the same to start with. Indeed, we have a mass m moving in the Cartesian plane under the action of two control commands, fx and fy, and we have the environment placed at a certain position along the x-axis. The x of the environment is equal to some constant c. But now we assume that the environment is soft, and we model typically this softness by the presence of a spring. It's like having a wall suspended with respect to a fixed wall with a spring of stiffness Ke greater than 0. So in this case, what happens? As long as x is less than c, then the environment force will be 0 acting on the mass, and so we have the free motion. But as soon as x becomes greater or equal than c, we will generate a reaction force, an elastic reaction force by the environment, which is proportional in the first approximation by the stiffness Ke positive to the deformation, so to the difference between x and c, assuming that x is slightly larger than c in the positive direction. So in this model, indeed we don't care too much what is the velocity with which we hit the surface. Moreover, the force will progressively be a continuous one from 0 in the free space. Then at the contact, when x is equal to c, we still have a force equal to 0. And then as we move inside, we enter, we deform a little bit the soft environment, we will have an increasing elastic force Fe. Now, you can also modify the environment model by adding a damping term, but the actual force will only be proportional to the deformation itself. Again, when you model this situation, you should make sure that the mass will not remain continuously in contact. So suppose that we are coming with a certain velocity against the wall, so we hit the wall, an environment reactive force Fe will be generated, and this will eventually balance Fx and possibly become even larger than Fx, which means that the mass will slow down, stop, reverse motion, and then be bounced back in the free space. As soon as x becomes less than c, we will detach. So this force, this spring force, will vanish automatically. So if we model this simple contact with a compliant surface, we should take into account this changing situation. Indeed, if the stiffness goes to infinity, we will recover the previous infinitely stiff situation with a geometric contact. But you can, I can anticipate to you, if you try to simulate the two situations, it is much easier to simulate a finite stiffness, although a very large one, than an infinite stiffness case in which you may have jumps of velocities when you're hitting the first surface with a non-zero initial speed. Okay, so these are the two situations. Now we move back to the previous one and try to generalize what happens in case of a very stiff environment. So this was the situation for this very simple case. What happens if we have a more complex contact situation? Typically, we assume that the interaction occurs at the end effector level, so we have an articulated robot, and we don't assume that we have applied feedback realization to reduce it to a unitary or any positive concentrated mass at the end effector level. But now we enter in contact with an environment surface which is not moving, so we still assume that there's a static environment. This is not always the case, but you can generalize this later on. And this, the geometry of the robot is, its kinematics is generic, and the environment is not a straight surface in general. It has its own nonlinear geometry as well. So as a simple example, again simple but already complex enough to understand that we need a general approach, we may consider a planar to a robot and its end effector moving in contact with a circle. So the end effector, as long as we have contact, is constrained to belong to a circular surface. Of course, this is one case. You may imagine a 3D case with surfaces of generic geometry. But the following development will apply to any of these cases as long as the contact is infinitely stiff, so that we can consider the end effector really subject to a constraint. So how do we model constrained robot dynamics? As I said, there are two possible alternatives. One which will end up with a model which has the same degrees of freedom or the same number of generalized coordinates, let's say, to describe for describing it, but in which we filter out or we project, in a sense, the resulting dynamics because of the presence of the constraint. So let's start with this general formulation. We have our model, dynamic model, M of Q, Q double dot, C of Q, Q dot plus G of Q. Again, we neglect any dissipative terms, so on the right-hand side we have only the applied torque by the motors at the joint. And we are interested in some output function which is related to the task, typically the end effector pose. So we have an n-dimensional vector Q, and we have a vector R, which is a function of Q, which characterizes the let's say the variable that we are interested in this interaction with the environment. Of course, R may have the same dimension of n or be strictly less than n. In any case, we suppose that these task variables are subject to a number of geometric constraints, bilateral, so in the form of equality, and we number this constraint as m dimension. And in this case, of course, m should be strictly less than n, otherwise we would bar the motion of the structure. Now, with this formalism, you can see that the constraint k of the vector constraint k of r equal to 0 may be applied at the end effector or at any other combination of generalized coordinates. So this is really, I would say, covering many instances of interaction. The most common one is at the end effector level, where r will be the end effector position or pose, depending on the space we are living in. So if we impose the constraint k on the r quantities, and since r are related to the generalized coordinate of the robot by the task function f of q, we can combine this constraint and write in k of f of q and baptize this new expression as h of q equal to 0. Now, in order to derive the robot dynamics under this constraint h of q equal to 0, which is an m-dimensional one on the n-dimensional degrees of freedom of the robot, we will use again the Lagrangian formalism. And in this case, we define an augmented Lagrangian, which is simply the original Lagrangian, so the difference between the kinetic energy and the potential energy of our robot, complemented by a linear function in terms of Lagrange multipliers lambda, which are an n-dimensional vector, multiplying the function h of q. Indeed, as long as h of q is equal to 0, this term does not perturb the motion, but in fact, as soon as we are trying to violate the constraint h of q equal to 0, some multiplier lambda arises, and this can be interpreted as generalized forces that prevent any attempt to violate the constraint. So the augmented Lagrangian is t minus u plus lambda transpose h of q. So we have n generalized coordinate q and m yet undefined multiplier lambda. So we have an extended space to work with, or an extended set of coordinates to work with, including now also the multipliers of Lagrange. Now, the Euler-Lagrange equation apply as well in this extended space, provided that we treat the lambda as additional generalized coordinate. So we write the Euler-Lagrange equation both in terms of q and of lambda. Indeed, in the augmented Lagrangian, q appears together with its time derivative, while multipliers lambda appear straight in a linear fashion without any time derivative. So when we apply the Euler-Lagrange equation to the augmented Lagrangian A, when we do the derivative with respect to q and q dot, we have in fact the same derivative we had with the original Lagrangian, and the extra term lambda transpose h of q is a function of q, so appears in the derivative of dLA with respect to the dq, so we have this extra term in the first equation with respect to the unconstrained case. And this is equal to the generalized coordinate, to the generalized forces performing work on q. Now, when we do the derivation with respect to lambda and lambda dot is not present, so this term vanishes. So we have only minus augmented Lagrangian with respect, partial derivative of the augmented Lagrangian with respect to lambda. And when we do this, we will get again h of q, because the augmented Lagrangian is linear with respect to lambda, and this is equal to 0. And this is again founding back the original constraint. Now the minus sign can be eliminated because this is equal to 0, but you can also interpret the fact that on the right hand side you have a 0 because the contact forces, namely the lambda, produce no work. So they are there only to react to attempt to violate the constraint, but they don't produce any motion. So on the right hand side in the Euler-Lagrange equation you will have a 0. Now if you do this computation, you will find out on the top equation again the same model that we had before. So m of q double dot plus c of q dot, the velocity term, Coriolis and centrifugal, plus the gravity terms. You have a u on the right hand side, and if you bring the last extra term on the right hand side and you do the transposition, you will have a matrix A transpose of q multiplying the multiplier lambda. And the A matrix is nothing else than a Jacobian. In fact, it's the partial derivative of the constraint H with respect to Q. And by the operation, you see that this matrix appears transposed in the star equation. This star equation will be used later on and on, so keep this in mind. We make an assumption. This assumption may be violated in certain cases, but in order to complete the modeling without singular cases related on how the constraints are imposed on the task variable of the robot, we assume that the matrix A, which is in fact a matrix which has m rows and n columns, because we are taking the derivative of an m vector h with respect to a q vector which has n components, so it's an m by n matrix, we assume that it will have full row rank indeed, because m is strictly less than n. So, under this assumption, we make another comment. Now, we have apparently no information on lambda. So we know that the dynamics will be similar to the one in free space. There's an extra term on the right-hand side, which are reaction forces to the attempt of violating the constraint, the geometric constraint, which appear as an extra function h of q of 0 equals 0. So how can we get some information about h? In fact, we can eliminate the appearance of the multiplier in the following way. Consider the constraint h of q equals to 0. This is a geometric constraint. It should hold, in fact, it's a form of holonomic constraint. This is the mechanical terminology, as opposed to non-holonomic constraint, which are differential constraints that cannot be integrated to positional one. Instead, we start with the positional constraint directly, and we make a differentiation of this in time. Since h should be 0 at all times, also the derivative of h should be 0. If we use the chain rule for this derivation, h dot is the partial derivative of h with respect to q multiplied by the derivative of q with respect to time, so q dot. The first is the Jacobian associated to the constraint, so it's h of q dot, and this should be equal to 0. And we do this differentiation a second time, because if h should be constantly equal to 0, then also the acceleration on time over time should be 0, so h double dot. So we make the one more derivative of h of q times q dot, and we have the usual form. Now, this type of derivation should be familiar to you right now, because it's like when we compute the acceleration of the second order differential kinematics, starting from the direct kinematics, is exactly the same. Now, this is in fact a matrix is a Jacobian, but it's not something which is related strictly or only to the task function associated to the robot, in particular to the end effector Jacobian, if we are constraining the end effector, but contains also the information about the type of constraint. So it's a specific Jacobian which relates the task variable of the robot with the geometric information on the constraint imposed on it. And we will see this very clearly in the following assumption. So we have this second order differential equation. The acceleration should satisfy indeed the dynamic equation, the constraint dynamic equation, so the star equation that we have just written. So if we substitute, we can always isolate the acceleration from the dynamic model, because the inertia matrix is non-singular, so we isolate q double dot from the star model, and we plug into this second order differential equation equal to 0. So we have a multiplying m to the minus 1, we have u plus a transpose lambda on the right hand side of the model, and we have brought also the other terms, non-inertial terms, on the right hand side, so we have minus c and minus g. Indeed, here we drop any dependence for compactness, and then we have the second term plus a dot times q dot equal to 0. Now in this term you can see that the lambda appears and is pre-multiplied by a matrix a m to the minus 1 a transpose, which is by assumption non-singular, because a is full row rank. So we can solve for the multiplier from this equation, and we can write lambda as the inverse of a m to the minus 1 a transpose, multiplying all the rest in the above equation brought to the other side. So we have a m to the minus 1, c plus g minus u minus a dot q dot. Now the the matrix, the full matrix multiplying all the dynamic terms, including the control input u, so c plus g minus u, is nothing else than inertia weighted pseudo inverse of the constraint. So it's a weighted pseudo inverse, and the weighting is given by the inertia matrix M. If you remember how this works, you have this explicit form. Indeed, it's the transpose of this inertia weighted pseudo inverse. So the expression of lambda can be rewritten in terms of what it is written. Indeed, at this point, we have an explicit expression of lambda, which is a function, pay attention, of indeed the parameter, the dynamic parameter of the robot, but essentially, in terms of variable, is a function of the state of the robot, so what is its configuration and its velocity q dot, but also of the input that we are applying. Which means that if the robot is in contact with our environment, which is modeled as a geometric constraint, so q is such that we satisfy the constraint, and q dot may be 0 or maybe a non-zero velocity, but such that we remain in contact with the geometric constraint. And now we try to apply an input, and this input may be consistent with the constraint or not. If it's consistent, then it will generate no reaction contact forces, so lambda will be 0. But if it's instead inconsistent, we will generate, as a function of also the input u, a multiplier lambda which is non-zero, which is the generalized reaction force which allows us to keep the constraint, to enforce the geometric constraint on the task value. So this is an automatic way of generating lambda. It should be clear that lambda depends not only on the state of the robot, but also on what we are trying to apply as input torque at the joint. Now let's take this lambda. You will see that many terms appear. C, G, and U are coming from the model. In fact, they are reversed in sign. So if we replace lambda in the star equation, we finally get the constraint dynamic model, which is again a set of n second-order differential equation, which takes this form. So m of q double dot, and now everything has been brought to the right-hand side. We had the original part of the model, so the u, which was already on the right-hand side, and we have brought there minus c and minus g, and this is the identity multiplying this term, but then there are all the terms coming from the expression of the multiplier. There was on the right-hand side A transpose times lambda. Now lambda has been replaced from the previous formula, and this is the resulting expression. Please check that everything works, including the suitable sign. Now, what multiplies, pre-multiplies the input torque u minus the velocity term and the gravity term from the original model is a projection matrix. In fact, this is a dynamically consistent projection matrix where a pseudo-inverse M is the inertia-weighted pseudo-inverse of the constraint Jacobi. And indeed, I am repeating here the expression of the multiplier. Now, you see that the presence of a constraint has, in this approach, has not reduced the number of differential equations. But we are filtering out everything we would damage or destroy the satisfaction of the constraint. Indeed, we make an assumption that we start at time 0 with this constraint dynamic model in a state that satisfies the constraint, which means that with the initial configuration of the robot, we are such that h of q of time 0 is 0, so we satisfy the constraint. If we have 0 initial velocity, there is no further imposition because we are there at rest. But if the initial velocity q dot of 0 is different from 0, it should satisfy also the fact that h dot is equal to 0, which means that the Jacobian of the constraint A evaluated in the configuration at time 0 times this velocity of the robot's joints q dot equal to 0 should also be equal to 0. So if this is the starting point, no matter which type of input we are applying from there on, from time 0 on, then the integration of the above model, so the computation of the acceleration from the constrained dynamic model, will such that we will continue to be consistent with the geometric constraint, so we will satisfy the constraint at all time. So this type of model is very useful if you want to simulate a constrained dynamic situation. So if you want to do the direct dynamics, so input u and find the motion under the presence of a geometric constraint. So let's apply this general formula. Let's take a look again. So m of q double dot, then we have the dynamically consistent projection matrix, which is I minus A transpose times the transpose of the pseudo inverse weighted by the inertia matrix of the Jacobian, and then all the other terms. Let's apply it to the first ideal mass case. And now we are assuming that at time 0, the mass is in contact, so x is equal to c, and it may or may not have an initial velocity, but if it has an initial velocity, of course, this should not be along the direction of x. So the generalized, using the notation of the previous slide to this case, the generalized coordinate for this mass m are x and y. The input command are f of x and f of y. The model of the system is very simple. In free motion, it's just the inertia matrix capital M q double dot equal u, where the inertia matrix is a diagonal matrix with the mass m on the diagonal. This as long as we are in free motion. Now that we are in contact and initially we satisfy the constraint, how is this equation being modified? First of all, we have to write the generic constraint, and the generic constraint is very simple in this case. So h of q is simply on the first coordinate q, which is the x, so it's x minus c equal to 0. And we make now the Jacobian of this scalar constraint, so the partial derivative of x with respect to the generalized coordinate q, so with respect to x and y, there's only x in the equation, so we have h of q equal simply 1, 0. And if we do the inertia weighted pseudo inverse of this matrix after some simple computation in which m simplifies, or the scalar m simplifies in this expression, then we end up simply with the transpose of A. So we have a very simple situation indeed for this ideal mass in contact with a straight vertical wall. Now, in fact, if we compute the dynamically consistent projection matrix, this computation is very simple. You can see it from what is written on the slide. Is simply given by a diagonal matrix with a 0 on the first element of the diagonal and a 1 on the second element of the diagonal, because we are subtracting A transpose times A pseudo inverse M transpose to the identity matrix, and this is the result, which means that all residual motion will probably occur on the second generalized coordinate, which is in fact what we expect. Now, if we also write the expression of the multiplier, so of the constraining forces, contact forces, the reaction forces that would arise if we try to violate the constraint x equals to c, many terms disappear, and what remains is just minus a weighted pseudo inverse with respect to the inertia matrix M transpose time the input u, which is again minus 1, 0 u, which is simply minus f of x. So, as we expected, if we apply a force Fx, a positive force which try to enter the surface, then we will have an opposite contact force Fe, which is nothing else than a multiplier lambda. Indeed, the same holds true if we try to get out of the contact, because we are now modeling a situation in which the contact becomes a bilateral constraint. Indeed, we cannot enter into this infinitely stiff surface, but we cannot even abandon because we are constrained to be there. So the lambda will be positive or negative depending on, so the f of the reaction force will be positive or negative depending if we are applying vice versa, a negative or positive f of x. So pay attention, there's a slight difference between what we have said before and the fact that now we are really constraining forever the mass to belong to the contact surface. Okay, so lambda in general can take both signs if we neglect the possibility of abandoning the contact. Indeed, this possibility is there if we abandon the contact, and this happens if we are in contact and we now apply an f of x which is negative, then the whole constrained robot dynamics will vanish and we recover the situation of the robot dynamics in free motion, so simply mq double dot equal u. Finally, the constrained robot dynamics, which uses the dynamically consistent projection matrix, is m q double dot, which the m is constant in this case, so there are no Coriolis centrifugal effect, there is no gravity indeed because this contact is on the horizontal plane, and then we have to dynamically project the input u, and this is multiplying u by the matrix 0, 0, 0, 1, so essentially extracting only on the second equation the actual command f of y. So the remaining, the constraint dynamic is nothing else in this simple case than moving along the y direction freely a mass small m by the force f of y. Now let's look at a slightly more complex example, namely the planar 2R robot that we have used as a more complex situation of constraint. So we start first from the constraint itself. There's no robot in the picture. So we are just imposing the belonging of some task variable r, so the coordinate x and y, to a circle with center x0 and y0 and radius r. So the r variable are x and y and should satisfy the equation of a circle k of r equals to 0, which is nothing else than x minus x0 square plus y minus y0 square minus r square, capital R square equal to 0. So this is the geometric constraint on which some variable r of our robot, defined in the Cartesian plane xy, should live forever. Now we put the robot in position, any position with its end effector characterized by the variable r, in fact, on the circle, and this end effector position is a function of the generalized coordinate of the robot by the direct kinematics. So we have r equal f of q and the standard direct kinematics that you are familiar with since the Robotics 1 course. Now, how do we write the full constraint? So h of q is just k on r, where r is a function of q, and everything is written in the slide. So the scalar constraint, the constraint is a scalar, so we have to combine the coordinate x and y of the direct kinematics, square them, subtract them the center of the circle x0 and y0, square them, add them, and then subtract the radius of the circle squared, and this is equal to 0. So this is in fact the geometric constraint that the two coordinates q1 and q2 should satisfy at all time. And you see that in this structure there is both the kinematics of the robot but also the geometry of the constraint, all in one single scalar constraint h of q equal to 0. Now if we take the time derivative of this, So we use the chain rule. So we take the time derivative of, the partial derivative of k with respect to this argument r, and then of r with respect to its functional dependence q, and then of q with respect to time. So we have q dot. So dq over dr is just looking at the geometry of the circle. So it will be partial derivative with respect to x and y. The capital R vanishes. So with respect to x, we have 2 times x minus x0. With respect to y, we have 2 times y minus y0. Then we have the second Jacobian, let's say dr over dq, but this is nothing else than the analytic Jacobian of the 2r robot in position. So let's call this jr of q. And then we have q dot. So if we now replace in x and y the expression of the direct kinematics, we have the final formula. And you can see that the Jacobian of the constraint, h of q, is in fact the product of two contributions, 1 by 2 row matrix, which comes from the geometric constraint, from the circle, and the Jacobian, which comes from the robot itself. So in this product, you have A of Q. And once you have this A, and you can take the derivative of A, you can have the dynamic model of the robot, you plug everything inside the system. Maybe we could go back to the previous slide. Oh, sorry. So you plug into the equation in blue, so you need the inertia matrix, the Coriolis and centrifugal force, the gravity term, and so on. But other than that, you have A, and you have A transpose, you have the inertia weighted pseudo-inverse of the A matrix, you have A dot, and then you can really do direct dynamics with this model. So you can simulate the situation for any applied force U. So let's go back to this situation. Okay. So with A, you have everything. This is why I don't proceed farther in the computation. Now, there's an alternative way of treating constraint dynamics. And the idea is very simple. You may impose the geometric constraint and use some of the generalized coordinate to satisfy the constraint, while the other remains free of use for describing motion in contact, so on this geometric constraint. So the idea, if you think a little bit, is very much similar to what we have seen in kinematics, and in particular in the redundancy, when we have looked for a way of satisfying a task while optimizing the function. And we had, in that case, two methods, the projected gradients and the reduced gradients. Now, this, at the level of dynamics, is quite a similar situation. You have, in the first case, you're considering your objective is being on the surface, so you're projecting the dynamics in such a way that you always satisfy the constraint. In the second type, when we use the reduced gradient at the time, we decompose the joint space in two sets of variables, the basic variable and the redundant one. And something similar we do now at the dynamic level. We use the constraint to locally solve, so we use the Dini theorem of the local explicability of geometric constraints to decompose the dynamics, although we are not now characterizing which are the coordinates that are free and which are the coordinates that we use to satisfy the constraint. We do all in one step. So, again, we start, so we will impose the M constraint h of q on the n generalized coordinate q, and we will reduce the description of the constraint robot to a reduced dimensional configuration space. And what is the dimension of this reduced space is indeed n minus m. So if we have a 2 degree of freedom robot like the Planar 2R and we impose a one-dimensional constraint, so m is equal to 1, we are left with a single second-order differential equation to work with. So we reduce, in fact, the number of differential equations. And we will see that eventually this method is more complex, requires some mathematics, in fact, and we will detail this also in a whiteboard slide. But it's very useful, more than for simulation, for designing a controller. And we will see this at the end of this few slides. So, what is the starting point? And here you immediately see the difficulty of this method, because there are some choice to be made, and suitable choice to be made. So we start with the Jacobian of the constraint, so with the constraint matrix H of Q. Remember, we assume that this is full rank, full row rank, so it's a M times N matrix. And we need to select a completion of this matrix in order to make it square. So additional n minus m rows as a function of Q in general, so this matrix will be labeled D of Q in such a way that the n by n matrix H of Q, D of Q is non-singular, at least for a certain range of value of Q. So this choice is not unique indeed, and it's the most critical step in this modeling. But suppose that you have find an expression for D of Q, and that this matrix is non-singular, so not only the rows of D are independent, but they are also independent from the rows of the matrix A, which are assumed to be independent from the start. So since AD organized in rows, one on top of the other, so stacked one on top of the other, is non-singular, then there exists an inverse. And the inverse can be partitioned according to the number of rows of A and D in terms of number of columns of the inverse. So the first M columns will be labeled with E, and the last n minus m columns of the inverse will be labeled with F. Indeed, these are function of Q as well. Now pay attention, in general, this inversion cannot be made symbolically. But you can, for every Q, assuming that the matrix AD is non-singular, do the inverse numerically and then have the columns of the inverse be labeled as E and F. Of course, they are implicitly function of Q, but you don't need to have their symbolic expression in general. You can have the numerical expression. However, if you have only the numerical expression, you cannot imagine to work with derivative of this function, as if you would do if you had the analytic expression of the columns of the inverse, E of Q and F of Q. And this will be apparent later on in the development, why I'm making now this consideration. However, now that you have introduced the matrix D and you have squared the system in a sense, you can define some pseudo-velocity V, in fact an n minus m dimensional vector of pseudo-velocity, which are the free velocity left in the picture. In fact, we define V as D of Q times Q dot, and if you have Q dot, a generalized velocity vector Q dot, you know that A times Q dot needs to be 0 in order to satisfy the constraint. However, because of the complementarity of your choice, D times Q dot will be the velocity or pseudo-velocity which remain free while satisfying the constraint. Okay, so this is why we are introducing V, and in fact we will see that the pseudo-acceleration, which are nothing else than the time derivative of the pseudo-velocity V, will be the only acceleration that appears in the reduced model. So let's write this acceleration, pseudo-acceleration, by taking the derivative of V, and we will have v dot. Again, we make the time derivative of the right-hand side. We will have d of q times q double dot plus d dot times q dot. Now this relation, so the map from q dot to a reduced number of pseudo-velocity v, can in fact be also inverted or pseudo-inverted, if you wish. In fact, we can always write q dot as f of q times v, where f is the second set of columns in the inverse of the matrix AD. And we will prove that this is true. So from a reduced number of velocities, the pseudo-velocities, in fact n minus m, we can compute also the full velocities, generalized velocity q dot, because we know that all this velocity satisfy the constraint automatically. This is the way in which we can proceed. Now, for the time being, accept that we can write the q dot as f times v, and from there we can write also the acceleration. And if we have the acceleration, we can use this acceleration, which are reduced, expressed in terms of the reduced acceleration v dot in the general model. So we will see that, in fact, the q double dot are obtained by differentiation of the expression of the q dot, so of f multiplied by v. So we will have f times v dot plus f dot times v. Now this f dot, for the reason that I've mentioned before, if you don't have an explicit expression for the inverse, you need to compute f dot numerically. But indeed, you can replace this f dot times v by the expression that you see in this slide, where the only time derivative that appears are of the matrix A, which is the Jacobian of the constraint, so it's something that you have in explicit form, and the derivative of d of q, which is the number of rows that you have used to complete a square non-singular matrix AD. In general, you may have d of q also as a function of q explicitly, and compute the time derivative accordingly. So now we need to show that q dot equal f of v is the right pseudo-inverse of the relation of the pseudo-velocity v equal d of q dot, and that in the derivation of the acceleration we can make the substitution of phi dot with the expression that you see on the right hand side of the last formula. So let's do this step by step on this whiteboard slide. So the starting point is that the inverse of the matrix AD is in fact expressed by E and F organized as columns. Now, if this is the inverse, then a number of properties follow from this definition. In particular, we can do two types of products of the matrix by its inverse. So if we do the product of the original matrix AD and then on the right of its inverse, namely of EF, and we do the block product, because of the being the inverse, we obtain an identity matrix. But if we write down the block product in this matrix, we have the first set of rows of the first matrix, so A times the first set of columns, E, so we have AE, then the product with the second set of columns, AF, and on the second set of rows, we have the product of the second block of rows, D, times the first block of columns, E, and then the second block of columns, so we have DE and DF. And we know that the result should be an identity, and in particular I am showing here the block dimension of the identity matrix on the diagonal. So we obtain in fact a number of useful identities, and we will use 3 of these identities. So the product A times E is the identity, the product of A times F is 0, and the product of D times F is the identity as well. However, we have also a second way of doing the product of the matrix by its inverse, namely having the inverse first and then the original matrix A, D, in the second position. So if we do this product, now this product is slightly different, so it generates automatically identity matrix n by n, but this takes the expression E times A plus F times D. Of course, all these products should be made properly by the size of the block matrices. So we have that the product E times A plus F times D is the identity matrix. So if we take the time derivative of this, indeed, being always the identity matrix, so constant, the time derivative will be 0. But the expression of this time derivative is obtained by making the differentiation of each term, which is in general a function of q, and q is a function of time. So we have E dot times A, I'm dropping now the dependence, plus E times A dot, plus if F dot times D, plus F D dot, and this is equal to 0. So this is an important other relation that we will use next. Now, the first things that I would like to prove is that we can invert the mapping from the n generalized velocity q dot to the pseudo velocity v, and this mapping is expressed by f equal d of q times q dot, as q dot equal f of v. And this is true because f is in fact the right inverse of the full row matrix df, because the product d times f is the identity. So we can write safely q dot equal f of v, and in fact the expression of f is analytical, so it's d transpose times d transpose q to the inverse times v. And in fact, that this is true is we substitute this expression of q dot into the original v d times q dot, and we obtain d times q dot equal d of f v because of this pseudo inversion. Df is the identity. In fact, we are using now from the above three useful identities the one that I highlighted now in blue color. So d times f is the identity, so dfv is nothing else than v, so we recover the solution. So in fact, this is a way of writing the inverse mapping using a pseudo-inverse of the original d. And we are using here, in fact, the fact that we have a full row matrix D, and this is necessary in order that the matrix A, D is a non-singular. Now, the second step is how we get to the simpler form in the derivative of this mapping. So we differentiate with respect to time the inverse mapping q dot equal f times v. So as I said, this is nothing else than phi times v dot plus f dot times v. But now v is again d times q dot. So in the second terms, we will recognize the product f dot times d. And f dot times d is one of the expression in the matrix identity that we have just written with a triangle there. And in fact, I have highlighted in green the f dot times d, and we can substitute this by in the differentiation by bringing all the other block products to the right-hand side with a minus sign. So in place of f dot d, we have minus e dot a plus e a dot plus f d dot. And then q dot, indeed, again, is a function of the pseudo-velocity, so we replace q dot with f times v. Now, in this expression, there is a further simplification. In fact, if you look, so you have the first term, which is there, f times v dot. Now, the first following product, e dot a times f v, in this product, you recognize the adjacency of a and f, so you have in fact the product af, and if you look at the identities that we have found in the first place, in particular, I have highlighted the one that we need in orange, so we know that A times F is in fact identically 0. So this term can be eliminated, and we end up with the formula that we have given in the previous slide. So the actual acceleration, the full acceleration of terms of generalized coordinate of the robot, when we are constrained on the geometric surface, it takes the form Vf times V dot minus E A dot plus F D dot times F V again. Now we are in place to arrive at the reduced dynamic model using this expression of the acceleration Q double dot. So we consider again the dynamic model subject to constraints, the one with the star, so mq dot q double dot plus c plus g equal u plus the transpose of the constraint Jacobian A times the multiplier. And here we have the same situation as before. Now we can massage this equation in different way. For instance, we can pre-multiply to the left both sides of this equation by E transpose. In fact, since since A times E is another of the equation that we have found before, is equal to the identity, so the transpose E transpose times A transpose is equal to the identity, so we isolate the multiplier. So if we pre-multiply by E transpose and bring the input torque on the left-hand side, we have E transpose, A transpose identity times lambda, so we have left with lambda. So here we have an expression for lambda. Another way of doing things is pre-multiply to the left both sides of the previous equation by F transpose and using the property A times F equals 0 that we have already used once. Now this in fact will eliminate the multipliers from the picture, because F transpose times A transpose on the right hand side is 0 and the multiplier are gone. So we have that F transpose MQ double dot equal F transpose everything brought to the right hand side, so U was already there, and minus C minus G, while the multiplier have vanished. Now this is in fact this differential equation are in number equal to the columns of matrix F. In fact, F appears as transpose, so this gives the number of differential equation that we are considering. So we are combining the original n differential equation of the dynamic models into an n minus m dimension. And we have still Q double dot, which is n dimensional, but we have found in the previous slide an expression of the actual acceleration of the generalized coordinates in terms of the pseudo acceleration v dot. So if we replace this into this equation, we end up with the following expression. There's a pseudo acceleration v dot on one side, pre-multiplied by a matrix which has dimension, in fact, n minus m times n minus m, and this is a positive definite matrix and is invertible. In fact, this is the reduced inertia of the robot when the robot lives on the geometric constraint. On the right hand side, we have all the rest, reorganizing terms, once we substitute the expression of Q double dot in terms of V dot and the rest. So we have F transpose U minus C minus G, and then all the terms that comes from the geometric derivation that we have done so far. So we end up with a reduced n minus m dimensional dynamic model. If the robot had 9 degrees of freedom and was constrained to belong to a three-dimensional surface, then 9 minus 3 is 6, and this would result in 6 differential equation of the second order. The second order is not explicit because you see only a v dot, but v dot is already a function of q dot. So in fact, sorry, v is already a function of q dot, so v dot is a function of q double dot. So in fact, this is a second order differential equation written in this particular form. So we have a way of describing the motion. We could also use this for simulation, and we also a way of giving an explicit expression to the contact forces, namely to the multipliers. And this is nothing else than what we have seen above when we isolated the multipliers, once we substitute q double dot with the expression of the pseudo acceleration v dot. And this is the second equation, which we give also a special sign because we will evaluate this later on. Okay, so this, as you can see, it's a much more complex procedure that we have set up in order to reduce the dynamics in the presence of a very stiff constraint that we handle as a geometric constraint on the generalized coordinate of the robot. Let's apply this to our simple example that we have treated before. So we start with the ideal mass. Now the mass is in contact with this stiff surface. We assume that x of equals c is the constraint, so h of q is x minus c equals 0, and again we have the same Jacobian of the constraint as before, 1, 0. So now we will compute the matrices and the terms that are needed to write down the reduced dynamics. So the first step that we have to do is to border the matrix A, which is a 1 by 2 matrix, with a second row in this case, only one row is needed, in such a way that this second row is independent of the first one, so that the matrix A, D stacked one on top of the other is non-singular. Now here the choice is trivial, because we can certainly choose D as the row 0, 1, so that we have the identity matrix. In fact, nothing is a function of Q in this simple case. And the inverse of this matrix is again the identity. And so we have also the columns E and F, explicit and constant. So any time derivative of E dot and F dot will vanish anyway, and this will simplify a lot the methodology. Now, the pseudo velocity will be d times q dot, so we are picking out only the second velocity out of the generalized velocity, the second component out of the generalized velocity q dot, which is nothing else than y dot. This simply means that the velocity which survives to this reduction is only the velocity along the tangent to the plane. So we can move the mass up and down arbitrarily, and this will be described by the reduced dynamics in terms of the pseudo velocity y, and of course the pseudo acceleration y double dot only, which are v and v dot by definition. So let's look at the expression of the multiplier first. When we eliminate all terms that are not present, c and g are not present in the original model. All derivative of the matrices A, D, E dot, E and F dot are all 0. So what remains is only E transpose times M F V dot minus U. And E transpose is E is the first column of the inverse, so it's 1, 0. So its transpose is a row 1, 0. And then we multiply the inertia matrix of the robot, which is a diagonal matrix with a M on the diagonal, is a small m on the diagonal. F is again the second column of the inverse, again 0, 1. And then we multiplied by v dot, which is y double dot, and then we subtract the u common vector, so fx, fy. When we do the product, we see that the first block vanishes completely, because this is 0, in fact, if you do the actual product. And what remains is just with a minus sign, 1, 0 multiplied by fx, fy, so minus fx. So again, we find the same situation as before, that the multiplier is the contact force and is equal to minus Fx, whatever Fx we are applying, positive or negative, and accordingly the multiplier will be negative or positive, so the contact force will have the opposite sign, assuming that we remain constrained to this flat surface at x equals c, so that the physically unilateral constraint is being treated as a bilateral constraint. So the mass cannot enter into the environment and cannot leave the contact with the environment. If it leaves, then you don't need the reduced robot dynamics, you need to resort to the full robot dynamics in free motion, so the equation that you see on top right, mq double dot equal u. So same situation as before indeed. And the reduced dynamics, again, we have the inertia matrix of the system reduced to the free motion left when we are in contact with this geometric constraint, and the reduced inertia is F transpose mf multiplying the pseudo acceleration v dot. Now if you do this computation, you end up only with the scalar m in this case times y double dot, and this is equal to on the right hand side, the only term that remains is F transpose u, which is nothing else than Fy. So I have highlighted the intermediate result, which is the reduced robot dynamics. And as expected in this very simple case, the only dynamics that matter, which is free of any contact force, is the dynamics of the y direction along the tangent to the surface. So my double dot equal f of y is the single differential equation that describes motion, while L equal minus f of x is the contact force that we have when we try to violate the constraint. In the planar 2R case, so this second bit more complex example, as before, we have already written the geometric constraint in terms of the task variable, which are the end effector position of the robot 2R. We have also written already the Jacobian of the geometric constraint, h of q, and we have seen that this is the product of a 1/2 matrix expressed in function as a function of the configuration q1 and q2 of the robot, times the 2/2 robot Jacobian. We assume here that we are not in a singularity, neither of the robot nor of the robot with respect to the constraint, so that A of q has full rank. And now the reduced dynamics require a feasible selection for a matrix D, so a 1/2 matrix, which stacked below the matrix A will give a non-singular matrix to be inverted. Now here it is more clear that things becomes a bit more involved, and we will make such a choice factoring out the robot Jacobian so as to separate the representation of the constrained motion from the possible singularity of the robot itself, of the robot Jacobian itself. So we assume, for instance, this would mean that our representation holds out of singularity provided that the circle does not touch at any point neither the outer border of the workspace, where the robot Jacobian JR is singular, nor the inner border of the workspace. In general, if L1 is different from L2, there will be a circular annulus as a workspace, so there's also an internal limit to the workspace, namely at the distance from the origin, L1 minus L2 considered in absolute value. If L1 is equal to L2, we assume that the circle will not touch the origin, so that the robot will, while circling with its end effector on the circle, will never cross a singularity, so that the robot Jacobian is singular. If it's instead, this is the case, the modeling will vanish exactly when we have a singularity of the robot Jacobian. But if we do this factorization, we are able to handle separately the singularity of the reduced representation, so related to the choice of D, from the singularity of the robot Jacobian, which will anyway destroy a complete modeling. So with this in mind, a choice, a very feasible choice for the second row of the AD matrix, so for the second row, for the row DQ that, by which we define the pseudo velocity in terms of Q dot, is the following, is minus 1/2 over y minus y0, and then 1/2 over times x minus x0, still multiplied by the Jacobian J of r. Why I'm doing this, I explained why I would like to factor out JR, and the remaining part, if you look at the first expression of the A of Q, is such that if you look at the determinant of the square 2 by 2 matrix A of Q times and D of Q, this determinant is in fact R squared, which is always different from 0, times the determinant of the Jacobian of the robot. So you will have non-singularity as long as the robot is out of singularity. So this is a good choice. And with this D in mind, you can also have the inverse, and the inverse can be given in analytic term once the inverse of the Jacobian is known, numerically or analytically. And the nice thing is that through the D, we also define the pseudo-velocity. Now, what is this pseudo-velocity? It's a scalar, in our case. And if you look at its expression, these scalars provide the value of the end effector velocity once you reduce this to the tangent to the constraint. In fact, the only velocity that the end effector can have that does not violate the constraint is moving it along the tangent to the circle. And in fact, this tangent is expressed exactly by dq times q dot, so whatever q dot you have. Okay? And in fact, the reverse is true. So the only feasible velocities which will satisfy of the joint velocity, so q dot, that will satisfy the constraint can be parameterized by the inverse of a velocity which is only tangent to the constraint at the given configuration. So if you write down the f with the previous expression, you realize that this is the Jacobian inverse times a direction of the velocity, of the end effector velocity, which is along the tangent and is parameterized in intensity by the scalar value v. So I could go faster or slower, I could move counterclockwise or clockwise along the circle, but all the velocities, feasible velocities for the joints, are parameterized by the scalar v, which is obtained by this expression. Okay, now this second way of modeling things is also well suited for not only for simulation but for control design. So we can do a reduced inverse dynamics. In fact, once you look at the expression of the reduced dynamics, so the one which in terms of v dot, which is pre-multiplied by the reduced inertia matrix F transpose M F, and you look also to the multiplier, so the contact forces that arises when you're trying to violate the constraints, then you have a very nice choice for the u variable that decouple and linearize these two expressions. So the reduced robot dynamics, the one that describes the free dynamics once you are living on the surface, and the expression of the multiplier, which tells what are the contact forces. So if you design your control law, it's a feedback linearization control law that takes into account now also the forces arising at the contact. So if you substitute this into those expressions, you immediately realize that you end up with v dot equal u1, so u1 is an additional command on the linear rise and decoupled system, and lambda equal u2. There's no dynamics here, it's an algebraic identity, but u2 will be the new command through which you impose forces at the contact. So, on the closed loop system, once you have applied the above controller, with u1 you move the end effector along the circle, for instance in the 2R case. With u2 you say which is the force that you would like to apply normal to the surface. So you have a decomposition in two directions. One is the tangential one, where you have free motion, and one is the normal one, where you have forces, and through u2 you apply these forces. For instance, if you want to move the robot in contact without applying any normal force, you just choose at this stage u2 equal to 0. And with u1 you specify which acceleration you would like to have along the tangent to the surface. If you plug these two values into the expression of u, you have a feedback linearizing control design that achieves the desired inverse dynamics. If you want to close the loop around this, then you will add an integral error on the lambda, and we will see this more in detail when we are dealing with hybrid force motion control, and you will add the PD term on u1, so not only the desired tangential acceleration, but also an error with respect to the tangential velocity and to the tangential position, once you have specified a way, a timing law through which you would like to move along the circle. I'm using the circle example because it is very clear. But indeed, if you look back at slide 24, which is the slide of the ideal single mass, then you recognize that there the dynamics is already linear and decoupled, and in fact you obtain exactly the expression v dot equal u1 and lambda equal u2 once you make the substitution v replaced by u dot, so that v dot is y double dot, u1 is just the force along the y direction scaled by the mass, so this is what you cancel of the dynamics, and lambda is just the contact force Fe, and u2 is the choice of minus f. In fact, with this, if you look back at this equation, you realize that you have an equation Fe equal minus Fx, which tells us how we assign contact forces, and another equation, which is the free motion, my double dot equal Fy, which is in fact the reduced dynamics. Okay, now let's go back to the other alternative. The second possible modeling choice when we have a soft environment is to model it as a compliant element. So we have already seen, and so we are coming back to the same slide that for which we had a preview, that in this case the compliance is modeled by a single spring of rigidity Ke positive. So in this case, when the robot approaches, it can hit also with a non-zero velocity the wall, the compliant wall. It will compress for a while the spring and then maybe be bounced back, as opposed to the case when Ke goes to infinity, so that this is no longer soft, but it becomes a very stiff and a geometric rigid contact, and then if we approach the surface with a non-zero velocity, we will be bounced back instantaneously. And as I said, this limit situation can be approached by this model once you bring Ke to the infinity. Of course, you cannot bring it to infinity. Numerically, you will use a very large value for the stiffness And if you integrate the equation, for instance, in Simulink, you will need a smaller integration step in order to capture this phenomena. The more and more as you go to Ke large. And in the limit, you may prefer to integrate the equation in a different way, namely separating the free motion from the contact motion, which is purely algebraic in that case. Now, I would like to comment on this because we will use later on this type of compliant contact situation for introducing a controller. In this case, we will use compliance or impedance control, and we will use impedance control not only in the direction where the system gets in contact with the environment, but also in the one where it's in principle free to move if there is no friction at the contact. So we will design impedance or compliance control in all directions, even in this simple two-dimensional case. Why is that? Because by doing so, assuming that we have a sufficiently precise but not fully precise information on the geometry of the environment, so we may have an uncertainty in the position of the wall, but also in its orientation. So if we are compliant or we impose an impedance model of behavior in all directions, we will handle also this uncertainty. Indeed, we expect there's a main direction where we will have contact and a main estimated direction where we could be free, but some uncertainty are best handled in this case by a full impedance control law. So I will come back on this discussion later on. Now, this model assumes that there's only one spring or one stiffness at the contact in every direction. Here in only one direction because we are on the plane and one direction is free of motion. Is this assumption true all the times? So let's consider a more general situation, slightly more general, and let's see when the robot environment contact assumed to be compliance can be modeled by a single elastic constant in each direction where the contact occurs. So the situation that we have just seen would be good if we have a rigid robot, and this rigid robot may include also a force sensor. Remember that a force sensor is always an object that has internally some deformation. When dealing with force or sensor, with the physics of measuring forces, we have seen that we need the deformation on the deformed internal structure of the force or sensor. We mount strain gauges, and through that we have an estimate of the contact forces. So some deformation is always there. This is why I'm assuming a rigid robot, including a force sensor, but when this deformation of the force sensor can be neglected, as opposed to how large could be the deformation of a compliant environment. So in this case, the K, the single elastic constant K, or stiffness constant, better said. Remember, elasticity is the inverse of stiffness, is given by the stiffness of the compliant environment. Indeed, there could be also a complementary situation. So suppose that the environment is quite stiff. So we assume that it is fully rigid. At this stage, if we have a force sensor mounted on the end effector of the robot, the compliance of the force sensor is the dominating one. So we can still model a contact with a rigid environment if the robot is carrying a force or torque sensor by assuming as the stiffness of the contact the stiffness of the sensor itself. So the situation is very similar. It's just you're replacing K. In one case, the dominant compliance is given by the stiffness Ke, and the other case is given by the stiffness of the sensor. Indeed, you may also have a situation in which you have a compliant environment, and you have also a sensor that is have a finite value of stiffness Ks. Now, so you have two springs in series, Ks and Ke, which may be of the same amplitude. Now, only if the intermediate mass between the two springs is negligible, then you can model this by a single stiffness constant. And in fact, if you have a series of springs with no mass or with negligible mass in between, what you do is, by principle of conservation of energy in a sense, you sum the compliances. So you sum the inverse of the stiffness. So the compliance of this type of contact when the mass is negligible is given by the sum of the compliance of the sensor and of the compliance of the environment. So 1 over Ks plus 1 over Ke. And if you reverse this in order to get the stiffness of the contact K, you will see that you have the product of the stiffnesses of the sensor and of the environment divided by the sum of them. And if one of the two is negligible with respect to the other, for instance, if the sensor stiffness is much smaller than the environment stiffness, then at the denominator Ks can be neglected with respect to Ke, and only Ke remains, which simplifies with the Ke at the numerator, and in this case the dominant stiffness will be of the contact will be given just by the sensor Ks. So pay attention to this way of reasoning. Indeed, if the intermediate mass is not negligible, then you need a model which assumes two different stiffness, so two different springs, not just one spring, one elastic constant, with some intermediate mass. So you will have a mass of the robot, you will have a mass of something which is in between. You may have also an extra mass for the environment if the environment is supposed to be not static, but can be moved under the action of the robot itself. So you will have a multi-mass, multi-spring, and you can include also damping in between. Now, the reason why we mount, another reason why we mount the end effect, the Forster sensor close to the end effector is exactly because we assume that with respect to the mass or inertia of the environment and with respect to the mass or inertia of the robot, what is in between the force torque sensor and the environment has a negligible intermediate mass. So the gripper, which is beyond the force torque sensor, with respect to the payload, can be neglected. In this case, the approximation of having only one constant of elasticity at the contact is reasonable. Now, along the same lines, I would like to show what happens when you are trying now to control force along a direction where you have contact and in which you may have some compliant behavior. Okay? So this is an intermediate situation. As I said, if you have an infinite stiff environment and the robot is stiff as well, so that there's no dynamics at all involved, everything becomes algebraic, then at the contact you have a contact force which is a function of the applied command and of the robot state. So you control force along the normal to this surface and you have free motion. So this is the hybrid situation. Now in this situation you have compliance, but suppose that in this situation where you have compliance in the contact, you would like to control the force, not just the position or something else. So there are a number of simple models that you can use, simple linear dynamic models, through which you try to capture the behavior of this situation. In fact, the models that I'm presenting here can be studied very simple under the presence of a simple proportional loop on the measured force. So we start from the following situation. Suppose that the robot can be modeled in just this single direction where you have contact with a mass subject to a command force F. There could be some viscous friction when this mass moves, so you have a BR coefficient of viscous friction, and the position of the tip of the robot now idealized into this mass, and we have already commented when this can be done through an intermediate feedback linearization step. The position is x of r. Now suppose that you have a rigid workpiece, so the environment is fixed in a certain position and does not undergo any deformation, but you have a compliant sensor. In fact, the sensor is always a bit compliant in order to measure forces. So if you have this situation, and you can also include some damping in the compression of the sensor, then the contact force is measured by the sensor and is Ks, the sensor stiffness, times xr, where xr is, you start to compute xr from when you are in contact. So when xr is 0, you have pure contact without compressing the sensor. If you're moving farther xr, then you will have a contact force which is proportional to the stiffness of the sensor to the deformation of the sensor itself, which will be simply the xr variable. You see that this model is very simple. Now, if this is the case and you would like to regulate, for instance, the force that you measure to a desired value Fd, then you can imagine to apply a simple control law which is proportional to the error between the desired force and the contact force that you measure, assuming that this is the model that can be used for this contact interaction. And you can tune the gain Kf in order to have a prompt response to a desired force with a higher Kf or a lower one, and so on. Now, people have seen that if you use this type of model, you may or you may not capture some phenomena that in experiment occur when you're trying to control the force in contact. In particular, if you increase the gain Kf and you look at the closed loop dynamics under this force control law, you will see that you will always have asymptotically stable behavior. Now, this analysis can be done analytically on the transfer function. These systems are described by linear equations, so the linear dynamic model, you can use Laplace transform and move into the Laplace domain with the transfer function. You can look at the localization of the closed loop poles when you change Kf, and for those of you who have a basics in control, there's a very nice method which is called the root locus method, which essentially parameterizes the location of the closed loop roots in terms of the control gain Kf. And there are very simple rules to draw qualitatively the behavior of this situation. Now, with this model, you never get instability, no matter how large you choose the positive gain Kf, which is not what happens in practice when you're trying to control forces by increasing the gain of the control loop. So, this author, Eppinger and Sering, many years ago developed a very nice methodology to capture this possible instability, introducing some extra dynamics. So they include possibly some compliance of the environment, so of the workpiece in this terminology, or some compliance of the robot itself, which is now seen as a rigid mass with direct command F. Now, if you assume, for instance, that you have some transmission compliance, so that you're commanding forces on the motor side, but then the link or the tip is moving after some compliance, so you introduce a spring, you split the mass of the robot in two. One will be the motor mass and one will be the link mass, and in between you have a spring. Then you can still have a simple model like this and understand what happens when you're increasing the gain by kf. And of course you can include one or the other, you can exclude one. So I will try to capture what is described in this paper, which is available for you as extra material on the course web page. For instance, introducing workpiece compliance. So working compliance means the following, that the contact is described, so the work is described by an extra mass mw, W stands for workpiece, which is anchored to a fixed position by a stiffness kw and another damping in general, bw. Now the damping can be eliminated in principle, but there is some damping somewhere. But let's keep with this. So when you're just in contact with a compliant workpiece like this, then xr and xw will have the same value, and suppose that this is the zero value for them. Now if you push on the robot mass with the force F, xr will increase, and this will compress a bit the sensor, which has a stiffness S, and this elastic force in the sensor will compress a bit the position of mw, depending on the stiffness kw. So xr will move together with xr. Since the sensor is measuring force through the compression of its equivalent spring ks, this compression is now measured by the difference between xr and xw. So pay attention where this type of forces is being measured. So once you modify the model. Now this is a system with two mass. You can write two second-order equations describing the force balance on this mass and their acceleration. So this system has two second-order equations. If you look at the Laplace transform between the desired force in a control loop and, or better say, even in open loop, between the commanded force and the actual controlled force Fc, you will find that this transfer function has, in fact, a dynamic of the fourth order, because there are two second-order differential equations. And there are also two zeros in the transfer function appearing. So when you're now closing the loop, these four poles, which are all asymptotic stable in the closed loop, will move as shown in the root locus diagram, will remain in the left-hand side of the complex plane, so the system will still be asymptotically stable. Two poles going to infinity along asymptote, which still remain in the left-hand side of the complex plane, while the other two poles will converge to the open loop zeros. This is standard results in automatic control of linear system. So even in this case, by increasing the gain kf, you will never capture an instability. So the authors propose another type of model. Suppose that the workpiece is still rigid, so the sensor is measuring just the compression between the tip mass and the workpiece, so the position x2, but you have some compliance in the transmission. So you have split the robot MR into masses M1 and M2. Of course, the total sum remains the same, so M1 plus M2 is equal to MR. Now you're pushing on the first mass, which represents the motor position, with X1. The K2 represents the stiffness of the joint, or at this level of this monodirectional dynamics. and this stiffness will be K2, or indeed when K2 goes to infinity, you recover the previous situation, so the two masses becomes the same mass. So you define new variable x1 and x2. The 0 is when you're not compressing the transmission and you're just in contact with the environment, so you're not compressing either the sensor. Now if you push with a force F, you will compress the transmission, so x1 will progress, you generate a force which is K2 times the difference between x2 and x1. x2 will move as well. The workpiece is not moving because it's fully rigid, but you will compress the spring and you will measure a force Fc. Now in this case, the system is again a fourth order system, so it has 4 poles, but indeed it will have no zeros in this case. So the 4 stable poles in the open loop, when you close the force control loop and you increase the control gain Kf, so the 4 poles will, there will be only 1 0 in fact, now I can see it. So 2 poles will go, one on the 0 and one on the asymptote, which is on the real axis, negative real axis, so this will remain stable, but the other 2 asymptotes enters the right hand side of the complex plane, so 2 poles will symmetrically with respect to the real axis diverge, going to the right hand side. As soon as you enter the right hand side of the complex plane, the system will become unstable, which means that if you increase the gain in order to have a better force control performance, you will get instability. And this instability is typically recognized in experiment by a shattering of the contact between the end effector of the robot and the environment. Indeed, if you put both situations together, so the compliance of the transmission and the compliance of the workspace, you will get a 6th order system, so 3 second order dynamics. So in the transfer function between F and the controlled force Fc, which now takes a different expression, you can recognize this by yourself. There will be 6 poles which are stable in the open loop, but once you increase the gain, you will get again instability. So the result is that if you have a stiff workpiece, a sensor, and also a sensor and a compliant workpiece, and you increase Kf, you remain stable for all positive Kf. Instead, if you introduce compliance in the transmission of the robot, no matter if the workpiece is rigid or compliant itself, when you increase Kf, sooner or later you will get instability. And this is a nice analysis that can be made. Of course, you can imagine other form of control force. You can introduce a feed-forward term of the desired force. You can introduce an integral term, and so on. And things may change, but you can still do a linear analysis that predicts stability or instability in the closed loop for this force control. Now, there are other tasks in which indeed you have multiple direction for the end effector, which is constrained in some direction, and in this constrained direction you can control force, but is free to move in other direction. Now, the type of contact may be very different, and in fact you require a general methodology in order to cover all these cases of hybrid control. Indeed, for having hybrid control, you should have at least 2 degrees of freedom that comes into play, and you control one Cartesian direction in force and one you control it in motion. So, for instance, this is a number of pictorial situation that you can imagine. So here you have the robot end effector, which is grasping the handle of a crank that can rotate. Now, if this is the type of interaction, you may imagine what are the degrees of freedom that you control in motion and which are the ones that you can control in force. We will be very clear later on, but this is just some introductory material that I will use to complete this general lecture on interaction control. So in this case, if the handle through which the end effector firmly grasps the crank is a free spinning handle, so it can rotate on its axis, the axis B, then you can freely move along the tangent direction to the circle that is described by the handle around the rotation axis A of the crank, but also moving or not moving the position B, you can rotate around the free spinning axis of the handle. So there are in fact two directions where you can freely move the end effector. And we will see that complementary to these two directions, there are four directions, generalized directions, so linear or angular, where you cannot move. For instance, you cannot move along the axis C, which is the axis of the crank. Why? Because this is fully rigid. So you're constrained. You cannot neither come closer to the axis A, nor bring the contact point B farther away, because otherwise you would crash the crank and the handle as well. So this is one direction where you cannot move, but indeed you can control forces. And if you push, the rigid system will react with a reaction force that compensates your push. And in fact, you can show that there are three more directions where linear or angular, where you cannot move, but you can impose forces. Indeed, you can also impose a zero force if you don't want to stress the structure. Now, still considering this ideal case of a robot turning a crank, you may have a different type of contact. For instance, the handle may have a fixed crank that does not rotate around its axis. So this is a top view of the same situation. Well, in this case, you can still move the crank and accordingly move the gripper and the end effector of the robot along the circle which is centered at point B. Okay, so you have 1 degree of freedom that you can freely control in motion. But then, because the contact is now different and the relative motion is not more allowed by the free handle, which is now fixed to the crank, you will have 5 generalized directions where you have reaction forces arising, and then those contact forces can be controlled. So you have a hybrid situation in which you have one direction that is free and can be moved, can be controlled in motion, and 5 directions which are constrained, and there you can control the reaction force, so the contact forces, and therefore the reaction forces of the environment. As you can see, depending on the type of contact, you have a multiplicity of situations in this case. There are also more general situations. In fact, we have developed a method a few years ago that covers also these cases. Consider, for instance, this, again, pictorial view. These are drawing by Costanzo Manes, which was formerly a PhD student of mine and now is a professor in the University of L'Aquila. So this is a robot that is pushing a mass along a guide which is constraining this mass, and this mass is suspended to or elastically coupled to a fixed wall through a spring. Now, if you look at this situation and you decide which direction are free of motion, and therefore you can only impose a motion there and no contact force, and which direction in fact are constrained to the motion, and therefore you can impose a contact force there because this will be balanced by the reaction of the environment, the situation is even more general. In fact, here, if you are able to move up and down this mass, there will be no contact force, no reaction by the environment, and so this is a direction of free motion. Now I'm not completing all the 6 directions, but just to understand that there are more type of possible motion. Indeed, in the lateral direction, you have a constraining guide, so no motion can be imposed, but you can impose a contact force because the environment will react, balancing this contact force no matter which is this value. So you have a fully rigid constraint in that direction. However, there's a third type of direction, which we call dynamic, which is the one on the direction where the spring is placed with respect to the wall. In this dynamic direction, indeed you can impose a motion. But if you impose a motion, the environment will react with a force which is a function of its own characteristic. So you can control motion and you return some force. It may be a good value of force or a bad value of force. This depends on the type of the environment. But in any case, you cannot control both. You have to choose if you control motion and then a contact force will result. Or you can choose, like in the previous example of force control, to control the force at the contact, and then the mass will move a bit as a result, and it can move slightly, or it will move large depending on the stiffness of the environment. So it could be a good outcome or a bad outcome, but in any case, in this direction, you can only control one of the two, either a force or a motion. If you choose to control the contact force, then the mass will move accordingly. So in fact, there are 3 types with 3 different colors by which hybrid task can be modeled and controlled when we have some dynamics of the environment. And we call this a generalized hybrid modeling structure. So there are 3 sets of possible direction in a given task frame. I'm introducing this example because later when we will cover the hybrid force motion control design, we will follow the more conventional set where these dynamics direction are not present, but in fact we could generalize this also to the presence of such type. And we set up a formula that can cover all situations and also combine situations where direction are not fully linear or fully angular, but can be also be specified as a combination of linear motion and angular motion, as well as linear forces and moments around the same direction. Okay, with this I have completed this long introductory lecture. The next time we will move to the specific design for impedance or compliance control, and later on hybrid force motion control. Thank you for listening.